Yeah, so we have been discussing generative models. These are the references for what we are discussing. And we discussed sampling. What is sampling? You are given a distribution P of X, where X is a random variable. It could be discrete random variable or continuous random variable. And you are given this distribution or PDF, probability density function. And then your task is to draw samples from this PDF. What is the utility? Utility is uh, generating random data to, let us say, find various statistics, mean, variance, etc., or just finding out how the data looks like. Or it could be more interesting things like generating new images, right? If I'm given images of a person and somebody asks me, can you generate more images of this person, or can you generate image of this person which is smiling or crying or angry, so basically conditioned on certain classes. So I can do that. So basically these are the different applications of generative modeling. So drawing samples from a given PDF. So if we know the PDF, then how to draw the samples. Of course, knowing the PDF or approximating the PDF is another problem, which we will be dealing in today's lecture. But let us say if we know the PDF, how do we draw samples? So in computers, we generally have a uniform random number generator, which is generating uniform a random variable with uniform distribution. So this is uniform distribution. And how do we obtain non-uniform distributions using this uniform random number generator? The answer is we do transformation of variables. Okay, if it is a discrete random variable, then the transformation is very easy. We just do the binning, and each segment uh, uh, will have basically, when my number lies between that range, I choose that bin and output that corresponding discrete label, right? And then we saw transformation of variables, which is very useful when X is a continuous random variable. And it's a very simple formula. Where is the formula? This one or this one? These two. Draw. So this is an important. This and this are two important forms. Okay, then this was one way we discussed quite in detail, and then multivariate sampling, that if our input is not just a scalar but a vector, then we can do factorization over different scalar random variables which are part of that vector, and then do ancestral sampling, or basically sample one by one using chain rule. Or I could approximate in, or I can simply uh, transform it into, what do you say, independent random variables and sample independently. And then we came to graphical models. So what are graphical models basically? So you have got uh, different random variables. So if you see, the joint distribution is a very complicated thing. Joint distribution is a very complicated thing. The number of tunable parameters, even for a simple discrete random variable, is also very difficult to find. So it has so many tunable parameters. So that is why we take help of conditional independence. And to represent conditional independence, I use a graphical representation, which is basically different nodes represent different scalar variables, and every node is dependent on some other nodes, which are called parent nodes, and this node is called the child node. So if x4 is my child node, its parent nodes are x2, x1, x3. So basically my probability of x4 given these parents x2, x1, x3 is independent of all other random variables, right? So it's conditional independence. This is what we discussed last week. Okay, let me. So this is what we discussed last week. Okay, now what we are going to do now is, let me see what is the next topic we have. Graphical models we have seen. Next I have okay, let's, I think I mentioned this term just now. Let me explain that term. It's called ancestral sampling. Now, if you ask me, can you sample data from this joint distribution? So how will I do? It's very important concept. It's called ancestral sampling. And this we do on graphs. Oops. This we do on graphs. So we have got this graph. Now, if somebody asks me, can you generate random samples from this joint distribution? It's very easy. How I will do? I will first sample my x1 from P of x1. Why? Because it is an independent random variable. Then I will sample x2, which is again an independent random variable. When I say x, this is a different distribution. This is a different distribution. And then I sample x3. How do I sample x3? X3 is also an independent random variable. So, okay, I can sample it. Basically, I know the distribution. Then I have to sample x4. Now, x4 depends on x1, x2, and x3. So, basically, I know P of x4 given x1, x2, x3. So I can sample my x4 from this distribution. And it's again here, all these terms which I'm not writing for brevity. And then in this way, I will continue until I get x7. And that will be my one x vector. My pen is giving problem. Okay, so my x vector is simply x1, x2, so on, up to x7. So this is, in this way, I got one sample of my vector x. Okay, and then I can again do the sampling. Now this is, see, this will be using this value. Just notice that this value of x1 is being used here, and this value of x2 is used here, and this value of x3 is used here. Right. So this is a conditional generation. Okay. So this is the concept of ancestral sampling. The general procedure is very simple. You start from the root. This is the steps. General general steps. Start from the root and progressively sample the children. So this is ancestral sampling. Anybody has any questions here? Okay. Now let me. Now I will be just discussing a bit about different uh, representations of graphical models. Why is thinking? So okay. So many times we have got latent variables. Likely all these x were my visible variables, right? And I can have latent variables as well. So whenever we have latent variables, so for example, I have got probability of p vector, or you can say probability of x vector. And I'm not able to find a very good graphical representation, but I represent it with a latent variable, probability of x comma w, where w is a latent variable. Oh, I don't know why my pen is hanging. So this is a latent variable, and you sum over all w, right? This is how you do. And now this thing you can sample. So, so you what kind of graph you will get? This is a w, and then basically you are representing this as okay, p of x comma w is p of x1 or xi given w. Sorry, my pen is hanging today. I don't know why. Product over I equal to 1 to capital N, let us say, into p of w, right? I can, so the model will be x1, x2, and all these are xn. So this model I can represent in short as this w, and this is my xn, and now there is a, this plate represents that I have multiple instants of n and the total capital N instants. So n varies from 1 to capital N, right? This is a representation, which this plate representation is just telling that basically Instead of drawing this diagram, I have a shorthand notation for this as this diagram. So they are basically equal. They are basically equal, means they are same distribution, just this is a simplified way of representation. This is used in the Bishop's book, PRML. So this notation is from Bishop. Okay, now we can have deterministic parameters, right? Deterministic parameters. So for example, you may have a distribution P of x comma w. Today my pen is really giving trouble. X comma w, and as you know, like you may have a sigmoidal distribution or some kind of distribution where you have some given parameters, uh, or there could be some observed values which are already known to you, maybe some observed values t, some or so some parameters like sigma, mu, etc. So how you can represent that thing? That thing you can represent like this. Now it's getting a little complicated, but please pay attention. So the distribution is like this, means the probability of W, and let's say W depends on, let's say there is some alpha also here. And just this is an example, probability of W given alpha times product over N going from 1 to capital N, probability of X of N given T of N, comma W, comma sigma, comma mu, right? Now, how can we represent this thing in the plate representation or in the graphical representation? We definitely need a plate. Now the latent variable, sorry, the observed or the deterministic values are represented not with a circle but with a dot. So I have a dot. This dot represents my known value, let us say T of n. So my x of n depends on T of n. Let's say if I have an x of n here, and this is up to capital N. So x of n depends on T of n. Okay, so there is a question, what is T? Okay, T is a observed value. And these parameters are like mu, sigma, alpha, etc. All right, so T are the observed values. So T of n. And then I have my x of n depends on T of n and W. And for W, there is no iteration, so it is outside. And it is also a random variable. So a circle, W. And what else my xn depends on? Some deterministic parameters, mu and sigma, which are also not dependent on n. So they're outside the plate. So we have mu and sigma. right? And then I have W is also dependent on alpha, and alpha is a deterministic parameter, right? So that is my graphical representation of this distribution. Clear? Okay. Now, okay, I want to, now we are coming to a very important point where we have to train our parameters. Where you want to train our parameters. How do we train our parameters? Okay, let me first copy this graph. Okay. To train, what are the parameters? Alpha, sigma, mu, right? To train my parameters, I have training data. Now, training data will contain what? Out of these things, training data will have what values? Please write on the chat window. Very simple question. Training data will have what values? Training data will have so will my training data contain sigma? Answer is no, because sigma is a parameter which we are estimating. Training data will not contain sigma. It has to be estimated from training data. Will it contain mu? Answer is no, it will not contain mu. Will it contain Tn? Question.
Yes,
Will
sir.
my training data contain Tn? Yes or no? The answer is yes. Yeah, because my Tn is anyways a known value, right? Means it is a known or observed value Tn, and what I don't know is the corresponding value of xn. That I don't know. So my training data will contain Tn. Yes, even my test data will contain Tn because this is the observed value for which we want to compute xn. Now, what else? Alpha. Will my training data contain alpha? The answer is no, it will not contain alpha. Not this, not this, not this. Now, xn. Will my training data contain xn? Will my training data contain xn? Yes or no?
Yes.
Yes, it will contain xn. That is why we represent this, we do a shading. We shade this node saying that this data is available during training. And this data is also available, but this is always available. So this is a dot. What about W? Will this be given in the training data? Yes or no? Will this be given in the training data? No, very good. Yes, because W is a latent variable, and latent variable is never seen. We mean it is just an assumption, it's an assumed quantity. You never observe the latent variable. It is just a tool for helping me in mathematical modeling or simplifying my mathematical model. Okay, very good. I think, thank you very much. Let's move on. So during training, we know this value. Now let's come to the testing time or the inference time.
Sir,
Yes.
sir, I have a doubt. Like we have Tn and we have Xn. So as you said, Tn is observed values. So what is the definition of Xn here?
Okay, I can give you one example. Let us say you are doing speech recognition, right? Very common problem which or you are doing, take a simpler example, image recognition. So TN will be your image, for example. XN is your uh, corresponding label, for example. But of course, in that example, W does not come into picture. In that image recognition example, ignore W for some time, and you have XN and TN only. There is no W in that example. So
Xn is
you
kind
know,
of label.
pardon?
Xn is a kind of label.
Yeah. Uh, in this example, XN is the label, TN is the image, input image,
Okay, sir.
right? So because ultimately you want to estimate probability of the label, probability of label given the input image and the model parameters.
Okay, sir. Got it,
Right?
sir. Thank you.
This equation is very general, and it could be used to model many different kind of phenomena. But I'm just giving one example that even classification problem is one such phenomena which can be modeled with this framework. Okay. You could
Yes, sir.
also have speech recognition problem where it is a time series, and you want, uh, or you could have audio event detection or speaker diarization or melody extraction. All these examples could fit in this framework. Of course, I don't know how you model the W thing because it's a latent variable, and you can create those kind of models. For example, your W could be, uh, let us say you are doing image recognition, then W could be some latent variable saying, oh, are these cars, or are these human beings, or are these, I mean, some latent variable which is helping you to model your X, right?
And sir, here alpha is hyperparameter.
Alpha is, it could be hyperparameter, or it could be a what do you say, tunable parameter, right? It could
Okay,
be
sir.
anything.
Okay.
Yeah, any kind of parameter which is determined for the model. Yeah. Okay, so now so let's say if it is a um, speaker diarization problem, then let us say you are um, labeling each frame with some with some label. So the frame parameters, like the acoustic features which you extract from each frame, will be your TN, and then XN will be your speaker label. Yeah. But then see, this one assumes that given Tn, your Xn are all independent, right? And in your speech or in your um, audio things, they may not be independent. Of course, you can model them as independent. That is your model. But if you model them with some dependency, then it might be a better model empirically. Okay, so okay, now we come to inference during test. Right? Uh, you are given a new, not Tn, let's say Tn plus one, or some T hat, means any of these notations you can use. So what will happen? Uh, Now, okay, so we knew this one. This is all training data, right? This was known. Now we have got a new. Just a minute. So during inference, what you want to estimate? You want to estimate probability of x hat given t hat, comma, your parameters, right? Sigma, mu, alpha, w, what else? That's it, right? So it's very simple. Once you construct this, then you can simply write here, I want my x hat, which is dependent on, this is my x hat, and it is deterministically dependent on sigma and mu. Sigma and mu. And okay, alpha is not directly dependent because in our original equation we don't have alpha conditioning x directly. See here, it depends only on tw, sigma and mu. So tw, sigma and mu. Okay, and then it depends on w, and it depends on the t hat, which is recently observed. Okay, that's it. So this is my inference problem. This is known, these are all known, and these I use to estimate these values, and then during inference I am finding out this probability. That's it. And if it is a classification problem, you know how to do thresholding, etc. Okay, now that's it. So we have seen now yeah, this is just a graphical representation. Okay, and generally you have seen Gaussian mixture models. In Gaussian mixture models, your W is for I can write here, for GMM or some latent distributions and discrete latent distributions. Your W belongs to a categorical distribution. Right, this we have seen. Your W is from a categorical distribution. So that GMM example can fit very well here. Okay. Yeah, that's it. So this was all about graphical models, and now we can move on to our next topic for today. I'll just stop the record.